A relation is any correspondence between two variables. There are several ways to define a relation. What we're going to start with is what we would call a numeric relation. A numeric relation can be defined by a set of ordered pairs, or they could be laid out in a table format like we see here. In this case, X is the year, and Y is the number of doctoral degrees received in mathematics in that year. So each one of these columns in the table is an ordered pair. Here we have, for example, 1993 as the X value, 526 as the Y value. This would be an ordered pair in the relation. Once we have established an X and a Y variable, we call the set of all X values the domain and the set of all Y values the range. So in this example, the domain is years. And the range is doctoral degrees received in mathematics. Or we can shorten that by just saying the number of degrees. Once we understand a numeric relation, this extends very naturally to a graphic relation because we can get from a numeric relation to a graphic relation by simply plotting the points. There are two examples here of how we can show a relation graphically. One is just by what we might call a scatter plot. In a scatter plot, we've done nothing but plot the points. In a line graph, we've taken those same points and connected them from left to right. So what we're going to do now is create a graphic relation based on the numbers that we were just looking at for doctoral degrees in mathematics. To do this, the biggest challenge is figuring out what scale to define on our X and Y axes before we start plotting the points. Because the numbers in this case make it clearly not possible to use a scale of 1 unit per tick mark, we have a little bit of planning to do before we get started. So the first thing we want to do is identify our smallest and largest X values and make sure that our scale on the X-axis includes those and maybe a little bit of buffer on the side. Since the X's in this case are in order, the smallest and the largest are very easy to identify. These go from 1990 to 2000. So to figure out what boundaries to use on the X-axis, it's kind of more of an art, I'd say, than an absolute science. We can either go exactly from 1990 to 2000, or we can add in a little bit of space if we want there to be a buffer. So I could say, for example, choose to go from 1989 to 2001 in this case, since I only need to span about 12 years with this, and I should have enough tick marks to be able to just do 1 year per tick mark on my X-axis. The Y values are a little bit more challenging. I want to identify the smallest Y in the data, which happens to be the first one, and then the largest Y value is not the last one, it's this 586 in here. So I want to make sure I include everything between 401 and 586. Before I can figure out my smallest and largest Y to use, I really should figure out the number of units per tick mark. And it looks like we're spanning a range of about 200, close to 200 here. So I might say 20 units per tick mark to get it down to the ballpark around 10 tick marks. Knowing that I'm using 20 units per tick mark, I can then say, okay, it makes sense to start at 400, or maybe it makes sense to start at 380, right? And to go up to 600. I won't really have a buffer in my Y's choosing 400, so maybe choosing 380, if we like having that buffer, would also be a good choice here. Okay, now we're ready to go ahead and mark these on our grid. Now I don't have to label absolutely every tick mark. I know that I decided to start at 1989 here. Maybe I'm just going to label the evens for the most part. This one would be 1990. I think I'll skip 1991 and go all the way to 1992. Skip 1993, etc. So I'm going to label the x-axis by marking every other year. Up to 2000. I won't bother marking 2001 since we don't have a data point there. And let's go ahead and start at 380 down here. We'll go ahead and get that buffer we were talking about. Each tick mark being 20, we can also label alternate tick marks here. Just as long as our scale is consistent, it doesn't matter whether our labeling is totally consistent. So since I'm going up 2 tick marks, I'm going to go up 40 here. Now up to 480. Now up to 520. 560. And 600. It is absolutely critical that our scale be consistent. Each of these tick marks on the y-axis is worth 20. Each of the tick marks on the x-axis is worth 1. That has to be consistent over the whole axis. Now I'll go ahead and start plotting my points. Starting with 1990, 401, that's very close to 1990 and 400. Going on to 1991, 461, that's very close to 460. Go ahead and pause this and try plotting your points now. I'm going to fill them all in just a moment. Okay, so I have a rough approximation of each of these points. We don't need to be extremely accurate on something like this. This is my scatter plot. Now as I connect the points from left to right, I get the line graph. So let's go ahead and do that. If you're ever unsure which 2 points to connect, just make sure that you didn't end up having to go backwards, where by backwards I mean right to left, in order to catch a point. And so we get a shape that looks something like this. We've chosen a pretty good scale for this graph because the whole graph fit, which is definitely important, and the graph is not stuffed all into one corner. We want to make sure that we're really using our grid. If we had counted our tick marks in advance and really tried to optimize, maybe we could get this to fill a little bit more of the grid, but it's pretty good. If we return just for a moment to where we planned out our scale, I want to call attention to the notation that's used in the textbook. This is graphing calculator friendly notation, but as we see from the example we just did, we can still understand and interpret this if we're not using a graphing calculator. We would say we're going from our lowest x of 1989 to our highest x of 2001 by a scale of 1 unit per tick mark, and then by our y min, which is, we used 380 actually, up to 600 by 20. So if you see this kind of notation showing up in a question instruction, this is what it's referring to. It's just telling you what scale to use on your x and y axes. The scale that we choose does affect how we interpret the information. If we look at the first graph here, these are computer-generated graphs, so perhaps the point plotting is a little bit more accurate. This first graph really allows us to, as accurately as possible, read points on the graph. And in math, that's usually our goal. So if I wanted to estimate something in here between 1992 and 1993, right, I could do that more easily on the first graph than I could on the second graph. But the second graph isn't inaccurate. It's also a good graph if what we want to demonstrate is that even though there is some fluctuation from year to year, it's not really changing a lot. So letting this scale on the y-axis go all the way down to 0 lets us see the relative change a little bit better. Generally, what we're interested in math classes is something more like this first graph, so that we can, as accurately as possible, see and estimate points on the graph. In addition to graphic and numeric relations, we also have symbolic relations, and all a symbolic relation is an equation in two variables. This also defines a correspondence between x and y. We might recognize this first one as having a graph that's a straight line. So this we could call a linear relation. But it doesn't have to be linear. It can be any kind of relationship between x and y. This second one is a circle. This may or may not be something that you're ready to recognize right away. With both the x and y variables squared, we're going to be something in the circle ellipse sort of family here. And since we have both x squared and y squared without any numbers multiplied by them, this is an equation of a circle.